Okay, good afternoon, everybody. So today we're going to jump into discussion on linear free energy relationships. What I'm trying to do next is bridge in, we spent first part of the class talking through how to do kinetic measurements, how to extract values like Ks. Basically that was focused on looking at things like time course to extract meaning behind a reaction, focused on this idea that either concentration or position in an equilibrium associated with the time point or concentration and change associated with a reaction are kind of the first part of extracting values. What we're going to do next with the linear free energy relationships is this is one of the first times we're applying measurements that come from Ks, right? So once you've actually done that first part, if you extracted things like K-obs, or you've done those measurements of change over time, this is where we start extracting meaning to them to actually sort of get other features in. So think of this as the application of once you've done your time course analyses. Now, we discussed this before. You guys have heard of linear free energy relationships. A very common thing about this, or just the general parameter here, is we're saying for some property of a reaction, like this is our fundamental thermodynamic equation, where if I measure the KEQ of a system and it's delta G, for different reactions, I get a property. The purpose of something like this is just a linear relationship that says, if I know something I can measure, in this case, like the equilibrium constant of a system, I can predict what the free energy of that equilibrium is. And again, so this is just a fundamental thermodynamic, but what's nice about that is this is a more easily measurable value than something like the free energy of that point. Usually what we'll end up doing, right, is a bunch of measured parameters here to infer what free energy changes are involved, and then using that for design or again, experimental modeling at that point. In general, the property we're going after here is saying, I will measure some quantity that may be either tractable, experimental, something that's useful, and I'm saying that the changes in the property I'm measuring is a direct linear correlation to some other unknown parameter I can't access. So it's all this point's focusing on this idea that measurements on one condition are going to have the same predictive outcome of another one. So this is just generally how we can use this both for explaining certain mechanistic components, but also designing new experiments. So the Hammett equation, the Hammett correlation is probably what you guys are most familiar with, or what you're introduced to as far as these linear free energy relationships. Historically, what this was is he was first basically studying how the acidity of benzoic acid could change as you changed the corresponding functional groups on that acid. So it was looking through and saying, can I come up with a systematic predictable chart that says if I change the para position of a benzoic acid, can I predictably understand what's going to happen with the acidity of that acid? So it's just a functional mapping of a property you can measure, like a melting point or a boiling point or something like that. Why this is super valuable is that if you come up with the standard series, it means that if I measured something like these guys and that one, and then I have something else in between that has another property, I could predict what that outcome would be without running the experiment. You can interpolate between those different points. So that was the goal. It also, the really cool part is the next big jump was saying that a measurable property like the pKa could actually be used for a rate constant property of a completely different reaction. And again, while it may seem pedantic, but it's one of those things of what Hammett was proposing is an equilibrium value like acidity could actually predict which reactions would or wouldn't work and how fast they would go. And that was a big jump at that time, because it meant, again, in terms of experimental reduction, you could do predictably an assignment of having a chloro in this position would have the similar outcome for both how fast a reaction might go, how stable something might be, how fast food may spoil. So it's a valuable sort of extension. It also laid the basis for certain things like the theories you see around resonance stabilization and things like that. You guys may have seen this where we use things like Hammett correlations to say, oh, if I see a certain Hammett value or a certain Hammett correlation, that is indicative of a certain kind of a mechanism, a stability of a tetrahedral intermediate or buildup of a carbocationic charge. So we're just going to touch briefly on where that history actually came from and how it sort of can be applied broadly. But you guys should be familiar with this. Is anybody surprised by this kind of general hand-wavy discussion? We say that if I have an electron donating group in the para position, it's generally going to destabilize negative charge in this position, which then is going to reduce the acidity of that carboxylic acid. So it's an A, B, C kind of correlation, right? Everybody's comfortable with that part. On the other side, same thing, right? Electron withdrawing groups tend to stabilize that part. So we can use this as a qualitative rank, that things with electron withdrawing groups will tend to be more acidic, things with donating groups will tend to be less acidic. What's really valuable though about the Hammett values is it could actually be used quantitatively, not just qualitatively. You could actually use this to put a very, very fine gradient or number on this, this correlation to actually come out with a quantitative outcome. So by going through and taking a series of these benzoic acids, you could measure the pKa's. This is an easy titrometric one. You guys remember this is your titration curve where the middle of that buffering region for these weak acids is where you define or measure your pKa. So that's an easy measurable value, which that pKa defines your Ka. You're not measuring concentrations, we're just measuring this as the intermediate titration point. And then that gives you direct access to your delta G's. So this becomes a molecular ruler for making the basis for DFT calculations and other parts too, right? So this is a simple quantitative value where measuring that allows you to access these two parameters, which comes back to, remember, that's your delta G is equal to minus RT ln KEQ, right? So having these ones are taking you back to your fundamental thermodynamic parameters. So that's great. That's a first kind of quantitative thing where we now have a value relationship as we go through this. And we're saying that these abstract things, you know, an amine, a methyl group, a bromine, this was the first way to sort of say, you know, how do I put a numerical representation to something as abstract as a certain functional group, right? Yes, we say nitro is withdrawing, but we can now put it on a rank that says nitro is more withdrawing than CF3, and by how much too. So you actually have a yardstick that you can start to use. And this was basically setting up a molecular ruler, like I said, to do quantitative measurements. Hammett's first jump was, okay, I've done these values. I now know that the stabilization of, let's say, my ionic state, if we're doing a deprotonation, we're starting from something that is neutral. We're going to go to an anionic system. We're going to imply that that's higher in energy because all of these are weak acids. We're not having a product favored equilibrium. Remember the capital K of all these is less than 1. So we're saying that all of these are starting material favored equilibria. It's a property of these kind of weak acids. So we're saying we're going up in energy here. And because of that, we are assuming that what we're really measuring is some kind of starting material state, the neutral compounds, have similar energies relative to each other. So we're basically, even though they're different functional groups, we're assuming that as we change this X group, the starting material energy does not change significantly. So that allows us to have a common starting energy that even if I go, let's say, from methyl, or if I was going to go through this and say on the blue curve, that might be where my para equals methyl, and then on the black curve, this might be something where para equals, since it's lower in energy, let's say nitro, right? The first assumption that we have to make is that your two starting materials are common in energy. That gives you a common reference point, which means is even as I change, let's say, my starting material substitution, they're similar in energy, which means that the KEQ value I see as different is this delta G value. We're using this as a common reference point, which means I can subtract the KEQ1 and KEQ2 to come up with a delta G difference between the two. So basically, I can define the difference in the delta G of two different energy states, and that's going to give me a gap between those two of what that the average energy difference between these two are. This is like Hess's law, right? If you know some value here, you know some value there, I can calculate this transitive property because A goes to B, B goes to C. So now I know something about A to C, right? Is what your kind of relationship you're building up. So again, from a qualitative way, this probably feels very normal. The thing I want to draw your attention to is look at this equation. The Hammett parameter, what he did here is he measured a whole bunch of different acidity constants, and he ratioed them against some unknown substituent. So he's saying, I will measure benzoic acid where para equals hydrogen, and then I'm going to measure other ones where I'm perturbing this group. And then it's the ratio of those two equilibrium constants, the log base of that. I'm defining that as a numerical quantity, this is my sigma value. So this is where the sigma, when you say that a group has a sigma value or parasigma value, the parasigma value numerically, its representation, it's the log of the ratio of the two equilibrium constants. So it's actually based in a real physical property. In this case, it's the equilibrium constants, the k's at your value, which means things like temperature matter for this, because if you're measuring that ratio of equilibrium constants, you're measuring equilibrium constants at a fixed temperature. That's going to change depending on what temperature you're dealing with. So it's a reference point that you have to keep track of. The other big thing about this too, this was one of the first times that direct measurements of things like these physical parameters have a lot of experimental error associated with them, especially with very small changes. One of the biggest things that Hammett started to do, and this is something that you see in a bunch of other applications, is ratioing things, right? By doing something like taking a similar system and doing this ratiometric measurement, it actually knocks out a whole bunch of systematic noise. So just by this kind of assumption that we've got this common starting material, that helps, but then expressing it as this relative ratio against your kh value meant that you had a lot more experimental precision in something like your delta delta G. It was much more useful to use on your average axis. So it's a strategy thing to keep track of. The last one though is if you look at this equation, all we really did is, I subtracted that from that. Remember, those are just delta G is equal to minus RT ln KEQ of whatever parameter. We're just taking the difference between two of those values. And then as we re-express them, we're getting rid of the ln, changing it to log base 10. That's where the rest of the numbers come in. So the part I'm trying to emphasize is that when we know these sort of sigma values, those sigma values are actually rooted back into a hard experimental value that we actually measured, usually as a ratio in order to take care of things like variation because of concentrations in some system. And in fact, in an experimental setup way, you will often do these where you could actually possibly measure two quantities in the same reaction as a competition. So not so much here. This is done independently where we take benzoic acids of two different ones and just titrate them independently. But a lot of times when we come up with these other kind of ratiometric measurements, for example, if we're trying to do little k, rate constants, you will typically run a reaction where I have two different substrates in the flask at the same time, and I'm measuring the relative rate between the two by taking the ratio of the two rate constants that I'm measuring at that same thing. Instead of independent experiments, you actually stack them against each other. So why this was valuable is because we suddenly had a way of taking individual structures, in this case your amine, your hydrogen, whatever your functional group is, in a specific position, and coming up with what we'd call a quantitative parameter. And again, it's not just a certain sign, like which one is bigger or smaller, but you could actually define jumps between the two. Again, this is at the moment, this is kind of stamp collecting. The big idea part was that you could use that information from a reference set of molecules, in this case, the para substitution for the benzoic acid, and I could predict the outcome of a similar equilibrium on a new set of molecules. So instead of saying, okay, I know how chlorine, bromine, methyl affects the acidity of benzoic acid, knowing that value, the sigma value associated with those specific molecules, I had a reasonable chance of predicting what the acidity change on a new molecule. In this case, I've now got a spacer, a CH2. So cool, what it means is there is a common relationship or common energy change of how does chlorine affect the relative acidity of benzoic acid, and can I transfer that to something where it's a new molecule, still an aromatic group, but now I'm adding a CH2 spacer. So the reason why this matters is no direct resonance here anymore. Now what you've got is, even though there's still an anionic charge forming up here, whatever group stabilizes that charge will have a similar kind of directionality to it. What was really big, though, was not just saying, okay, qualitatively, chlorine is withdrawing and will help negative charges. What he found was there was a value you could define known as the rho value. And the rho value was the slope. So saying that, remember, if what we measured here was the acid equilibrium constant, so what we're expressing on this value here, this is the log base 10 of the acid equilibrium constant for some substrate for this molecule. That's what you're putting on this axis. So I'm going through and I'm measuring on my y-axis the ratio of my, my acid equilibrium constants for this new substrate using the same substitutions as I have defined for my sigma values. Remember that down here, these sigma values are just log base 10 of your Ka of X versus H, where these come from benzoic acid. So really what we're saying on these two axes is, how does the acid equilibrium constant, this ratio for a new substrate, compare for the same series of this X substitution against benzoic acid? So having a value, a rho value of positive, means they both go in the same direction. In other words, a chlorine will sufficiently acidify benzoic acid and sufficiently acidify this homobenzoic acid. What is that one called? What's the IUPAC name of the CH2 skipped? It's like a phenethyl, right? Having the methylene between the two.
Benzoic acid.
Is it benzoic acid? That works. It's probably close enough. But yeah, basically we're saying that two groups of functional, or two groups of molecules has a similar trend associated with it as you go through and vary this X component. So that's the sign. Sign means that one group affects the other group in a similar capacity. The magnitude is basically a correlation coefficient. If the rho value was 1, you're saying that the magnitude that chlorine helps acidify this new substrate is exactly the same as how much it acidifies benzoic acid, then we'd get a rho value of 1. Having a rho value of 0.5 means it's going in the right way, but it's less sensitive to the substituent effects as benzoic acid has. So less than 1 means that the benzoic acid substituent, which is on your x-axis, has a larger impact in whatever you're changing compared to whatever's on your y-axis. You could extend this out where, once again, if I go through now to 2 substituents, you still get a positive rho correlation, but the value now drops to 0.2. So what we're saying is, once again, those substituents do help acidify these new substrates. It's just that as we walk this value out, as we move each CH2 group in, what's happening is the rho value is getting more and more closer to 0. The correlation coefficient drops. So why this mattered is you could now go through and say, I have a quantitative ratio, a way of telling me, as I add CH2s to my molecule, how much is that impact of that chlorine still being transmitted through the sigma skeleton. This was a way of actually starting to measure how much, when we say inductive effects happen, we can start to put a ruler on there and say, as I move this further away, that's the magnitude of the inductive effect I think I'm going to see. This is where it bases things like the NMR shift of the CH2 in this position as I change my chlorine is predictively going to change by a certain value that's measured out by this rho factor, right? Like, what you're measuring here is the impact of things like electron density through the sigma skeleton, bond polarization. So it's not just, oh, it's plus or it's minus, but you could actually put a value and say, predictively, I'm only going to get 20% of a bump in acidity if I have these 2 methylene spacers, compared to over here, I'm expecting a 40% bump in acidity as I go through the same point. So that value, that correlation coefficient, can actually be used in predictive ways to design out particular molecular structures. So if you're looking at things like, I'm trying to build a new ligand, and I want that ligand to have a tunable way to say how I'm transmitting, let's say, an effect over here, you can use something like your rho value to suggest, should I be using this, this double CH2 skip versus the benzoic acid kind of one. If you haven't seen it now, there's a couple of papers back in sort of the chemical literature, which are sort of like the most referenced papers of all time. This is pretty close to one of them, right? This is the original sort of like Hammett, Chem Rev type paper on this whole concept. So just in general, what we now have is a way of saying, I can correlate a ratio, this log of K equilibrium constant over equilibrium constant. So I'm doing a measured value of a substituent against a hydrogen reference. That value I'm going to define as my substituent constant, where this rho value over here is how your correlation coefficient. How much does this new measured impact mirror what we saw with whatever was used as my basis set? And again, the original sigma values were all these para substituents, and how does the para group affect the acidity? Yeah?
Have there ever been cases where you've been looking at like a more complex mechanism where you have the same, you
Absolutely. That's where we're building to next. Is all of this started off by saying, I'm going to measure a single transition state based on equilibrium, acid-base deprotonation. That's an easy one to do. And I'm going to make the assumption that changing things like that para position to these other groups will have either the same or opposite impact to whatever I'm doing on this other axis, speed up or slow down a rate, but also the same gap. So going from nitro to chlorine on benzoic acid gives you whatever, like a 2x bump. Well, what you're looking for is, do I expect to see 2x or 5x or 0.2x on whatever my responding variable is, right? So it was originally applied in this kind of way of, let's go and measure and quantify the whole universe. This is like a whole series of, I'm going to actually be able to tell you what the inductive potential is by using this kind of molecular framework point. But it started to actually open up a whole bunch of other cool things. For me, the biggest jump, and again, this is one of those things that hold on a second. Where was that? Bloop. Yeah, extended values. No, it's there. Rate constants. Being able to say that, look, okay, I can measure how one equilibrium is affected by this reference equilibrium. Fine, that's just saying acidic is acidic or basic is basic. Fine, that seems pedantic. The weird one was you could use an equilibrium value, how much does my benzoic acid get more acidic, to predict how might a rate change based on some other part here, right? And this is where you guys may have seen that things like SN1 and SN2 reactions at benzylic centers can be predictively correlated against the para values here. So, for example, esters, where a benzylic ester will hydrolyze faster or slower depending on what you do to that sigma value. And we can use that correlation to say, all right, if a nucleophile has to attack my carbonyl, and if pulling electron density speeds up that reaction, I can infer that somehow that para position is helping to lower that transition state. So it's not just talking about equilibrium positions, intermediates, but now you're starting to talk about transition state and how they affect it as well too. So you can ratio either small k, rate constants, or equilibrium constants and still correlate them back to some sort of an actual value. In general, what we're saying is that the sign of your rho value gives you sort of a directionality. And remember, when you're repeating this to yourself, the rho value being less than 1 or greater than 1 means there's the same pattern relative to benzoic acid's acidic constants. And then other direction is opposite relative to benzoic acid constants. The reason that I say that is that these initial ones were all based on these kind of your sigma values you have here are that reference set of the acidity of benzoic acid. But after this sort of correlation came in place, what they started to do was actually expand it and say, well, wait a minute, what if we go to other substitution patterns? What if we go to a meta substitution pattern or even broader from that one? The reason what changes, right, is if you move that position over to the meta position, you're not actually doing any resonance stabilization anymore. Now, by having a group in the meta position, you're looking at really an inductive potential rather than resonance and induction. So what they realized here was that, sure, this first sigma value, these kind of para sigma values were very useful. That's these kind of original OG values. But then going through the same substate where you actually have a meta substitution, you're now isolating stabilization that is primarily due to induction, not resonance. And now you can use this as a comparison to say, in the para position, I have both induction and resonance. And in the meta position, I really only have induction. So now you can start to separate and say, I can now take a mixture value and also separate out that component. This is where they started to extend out to these other sort of sets, again, not going too far from benzoic acid. But what they really did is they started to focus on stuff like this. If you take the sigma values of an entire series of groups, so chlorine, fluorine, and on, what you notice is there's a whole bunch of those groups that actually line up really well between their, over here, these are the sigma values, the sigma para values. Over here, this would be the sigma meta values, for example. Now, if in both of those cases, all you're measuring is induction versus induction and resonance, if everything was the same, so basically adding a chlorine group acidifies equally as well in both the meta position and the para position, you're saying that I'm basically measuring only induction in that case, right? That everything that's like meta is supposed to be induction only, para could be both. If they agree with each other, in other words, there's the same jump along that line, there's only really induction in that part. What you saw in this graph, though, is that groups like cyano or nitro that have these very large other resonance components, they lie off the line. So what happens is a meta, taking the meta value for a group like nitro or a group like nitrile, they are way more acidified in the para position than they are in the meta position. So what they started to make an assumption is, okay, anytime where there's this disagreement between these two values, I can actually correct that by saying there's some offset that I have to apply in order to get it back on the line. So as long as we think of, remember, all of these things are ratios of actual K values, there's actually delta G's behind them, that correction factor you had to apply could be carved out as saying, look, my sigma para value is the value I measure. The corrected sigma para value, what you're calling these para minus or para plus, what you've done is you've done this kind of meta versus para correlation, and you said that my real para value, if I'm only looking at induction, has to be corrected by some factor. I have to add a value that says, well, the extra acidification is this combination of both sigma and correlation of both the inductive potential and also the resonance potential. Again, part of it, I only want to mention this, is if you've seen different values, if you've gone through sort of Merck handbooks, you may be familiar with stuff like, okay, you've got your sigma para, your sigma meta, now you've got these things like sigma para minus, sigma para plus. Anytime you get to something where you're getting these other values associated with, where you're seeing sort of these minus and plus, these are transformed values where they've done these correlations and then added correction factors associated, where what they're trying to do is say, the real para value, if you only are looking at, let's say, a resonance effect, is better reflected by using this other scale, right? So this is where they're taking multiple linear free energy relationships and mixing them together to come up with a new set of scales associated with them. That's where they come from. The reason I point to it is because I remember when I first saw it, it felt like a lot of black magic of like, okay, you're saying that there's just this correction value you're putting onto it. Well, no, the reason behind it is they're actually assuming that the numerical value that they've applied from their acidity constants are solid enough that this para versus meta correlation could actually be used to add a correction factor that is still quantitative. They've done the same thing for the what's now called the para plus scale, where that allows you to actually go and do corrections of things like the inductive effects and hyperconjugation effects of certain parts. So I guess the bit of comfort I'm trying to put on, everything we told you back in second year about these are why these stabilizations happen, they come from measurements like this, these correlation values at some point of why we think something is bigger than something else. Or if we've given sort of a rule of thumb about, well, a T-butyl group is much more bulky than something else, it comes from these kinds of relationships to put them on some sort of a quantitative scale. So these extended values started jumping out much broader. So in the 1950s and beyond, they started using it for things like field effects. So if I put a charge group that is separated at a distance, how does that impact the stability of other sort of centers as well too? All I'm going to mention through again is if you go back to some of these primary ones, during the sort of the 40s, 50s, and 60s, there was this huge rush about people setting up reactivity parameter scales for all sorts of different reasons. So if you start to go back to some of these other more bespoke ones, things like these weird ES values and things like that too, you kind of have to go back into the literature to figure out why they were building it, what their reference was, and what series of measurements was behind that point. So I guess what I'm commenting on is, as you go beyond just the standard sigma values or sigma plus and sigma minus, you do have to spend a bit of time understanding why that linear free energy scale was created, what its purpose was, in order to make sure you're applying it correctly. So for anybody who's done like DFT calculations, you know B3 lip, right? That's your basis set. You know you should not use B3 lip to calculate something like a copper complex or something, because the functionals that are in that model are not appropriately describing the molecule you're trying to do. It's a similar capacity here, is you shouldn't be using, let's say, the sigma value if you're trying to really focus on a steric parameter, because it's really talking about electronics, not sterics, right? But yeah, the big jump over was if we can use these on equilibria, We can also use it to predict changes in rate constants, which means instead of just saying we're measuring delta G, we're measuring delta G double dagger, or differences in delta G double dagger. The form is really the same. It means that we would go through and measure the rate constant of one reaction, the rate constant of another reaction. I take a ratio of those two, log base 10, and I'm applying it to my sigma value from, let's say, your parasigma values or whatever, where the rho in this case is talking about how the stabilization or destabilization of that parasubstituent impacts the stabilization or destabilization of the relative transition states you might have across this one. But it's still coming from this, this kind of ratiometric measurement. Again, to me, this feels magic just because you're actually, fundamentally, you're measuring a delta delta G, right? You're measuring an energy difference between two transition states. And unless you've got the ability to measure your actual K values, you can't access something like this. So your rate constants and your ability to extract K obs is what feeds forward into an actual delta delta G value. And again, for anybody playing with computation, it's the single closest you're ever going to get to proving that your transition state you computed was real, because you can come up with two transition states of two competing pathways. If it matches against something like this, you've really got it. Like if you get a measurement from your two competing K values that matches a delta delta G, your DFT is actually quite believable. Because one of the problems, and again, you guys know this from any DFT work, the problem you have is you can draw a structure and say, here's the energy. That's an unbound energy that's just saying, fine, it's a value. But this is where you have to come back to things like Hess's law. The individual value you compute is kind of meaningless. The relative value against a reference standard, that delta, is probably accurate, because any experimental differences and errors in that computed value is carried forward in your two different models. So the ratio between the two is actually a meaningful value. That's where coming back to something like this still grounds you back in experimental reality. The one that I mentioned before, the hydrolysis of something like a benzyl ester has the same sort of correlations, where if you have a more electron withdrawing group, the rates increase, and the donating groups decrease the rate constants associated with that too. And again, what we're really getting into there is things like, this is where you see arguments like, if I see this positive rho value from my parasigma values, I am having a transition state that has a negative charge buildup. Because what we're really saying in that case is the parasigma value is talking about stabilization of anionic buildup, because I'm talking about acid-base equilibrium. Here, what I'm talking about is, well, I'm nucleophilically attacking a center. I'm building up this charge, so this electrophilicity parameter is really what I'm extracting. So a negative, having electron withdrawing capacity here is going to help you to speed up this thing because of a transition state that has other negative charge associated with it too. Now the problem you run into is where you start to get to two-step transitions. Like it's something where the reaction, even in something like this hydrolysis, we have a starting state, we go to a transition state to a common product, and then over to our final hydrolyzed material. There are cases where if this reaction is much more complicated, multi-step, changing this has to impact the same rate determining step in order for this to make sense. What we're saying is, as I go through and I change that para value, I'm hoping that that change in my para value is really only perturbing the same transition state by the same factor. So I'm moving them back and forth. But you know this on a surface, it's possible if you have a multi-step transformation, adding a certain functional group may help one transition state and hurt another one. So this is where you can get shifts in the rate determining step as you go through these values. So it is a little bit of a caveat. What you can get is changes in which one you consider to be your rate determining step as this happens. If you flip over, this is the other major one that you probably have studied, where if I'm doing an SN1 type reaction, so starting on an SN1 type reaction, I'm building a carbocationic intermediate. Because I have a carbocation intermediate with a common rate determining step, depending on what that is, I'm going to see a sigma value, a rho value associated with this that's going to have the opposite sign as what I would see with the hydrolysis one. So going through what would be a nucleophilic attack or an anionic transition state should have the same sign as your rho value for your sigma para values, because both of those are talking about buildup of negative charge. Something like your SN1 reaction, you're building up cationic charge, so since you're building up a positive charge, your rho value here will have the opposite sign associated with that part of it. So what you see is this opposite correlation. And again, going through and checking those sigma para and sigma meta values, as we're a lot of what we say in those kind of what you may have heard about relative stabilization of different carbocations, all those kind of broad claims that we've been making about what functional groups have in terms of relative ranking comes from these kinds of original primary measurements. So in general, for the rate constants, the same rules apply. You know, your rho value is predicting a same pattern of stabilization relative to benzoic acid if it's positive, or opposite if it's negative. And again, the best example of that is the substitution reaction onto benzoic acid for hydrolysis if it's anionic, or SN1 buildup of cationic charge if it's opposite. But yeah, the problem that you really run into, and we won't get into a lot of these other examples, if you have a multi-step transformation, and if changing your substituent actually changes where that rate determining step is, you no longer get nice linear correlations. You get what's called breaks in your linear free energy relationship plots. Effectively, what can happen is if I'm plotting out my sigma value, and I'm doing some, let's say, log of kx over kh, I might see a trend of forming for some part of it, and then suddenly I'm going to see a divergence. So often if you get something where as you're moving through a substituent series, instead of seeing a simple linear correlation, you get these breakpoints. One is sort of this curvature down, and then curvature up and then curvature down are the two kind of components. So these kind of forked ones, what happens when you see these kind of breaks in a trend, these are often indicative of you have a multi-step transformation. Whatever you were changing on the left side was following a certain pattern, and then suddenly, as you go through that break, you've switched over to a state where the change that you made has now made a different rate determining step in your system, and it's now responding to that new part. So we kind of have these three big buckets, right? We say that we go through a parameter estimation and a measured value. I'm looking for linear positive, linear negative, and the magnitude. And then the last one, very often you'll see, is this one, where you're getting these kind of curvatures or change in direction, which is indicative that you've got a much more complicated system where you've now changed what matters, right? For one of the things I'm going to have you guys work through on your next assignment is going to be giving you a couple of these values and sort of talking yourself through how does the change that we're talking about and why that sort of has an outcome in the linear free energy relationship you're seeing. So the one thing I wanted to focus on as far as an application comes back to some of the things that we've done around the lab. Long ago, one of the very first sort of studies that we ended up doing was going through this mechanism. It's like a Nazarov cyclization, so you're going through a cationic intermediate. And if you go through to kick this reaction off, the nucleophile that we're using here, we had a functional group that we're going to be manipulating. So going through and changing that functional group, what we're doing is we're really changing the nucleophilicity of one of our species. And what we wanted to see is, as I make that nucleophile more electron donating or electron withdrawing, how do we help or hurt this reaction? What we saw was a correlation like this. So we're seeing this case where, and again, I'm plotting these ones not as a log ratio, but just a simple ratio of our Ks. What we're getting is that more electron withdrawing groups in that position tends to go faster, and electron donating groups go slower. So this was opposite of a correlation that we'd normally expect if the nucleophilicity was the real important step here. What we're seeing is some other impact where somehow what we expect to be the nucleophile is actually changing the overall rate of the system. What we were testing, though, at the same time was two different possible catalysts. So this was part of a much deeper study where the question being asked was, if you did this rearrangement using a Bronsted acid catalyst versus something like a dysprosium or a transition metal catalyst, are you seeing totally different mechanisms? Right? So this is a question where, is it possible that because you're doing this through a simple proton versus something like a dysprosium or samarium, are they different? The fundamental mechanisms were very, very different, but what we got from a correlation like this is the substituent effect that we change fundamentally has exactly the same overall outcome between these two types of catalysts. So it was a very quick spot check to say, even though that the overall reaction profiles, the relative selectivity, the relative rates of these two different, like TFA versus dysprosium catalyzed systems, were very, very different. By changing the nucleophile component, we got the same sort of overall effect. So it's a way of looking at this and saying that the underlying mechanism, the transition states that you're probably dealing with, are probably related to each other, right? Especially seeing a type of a correlation that lines up quite to that effect. The one I do want to jump over is over to this. So has anybody heard of a guy named Herbert Meyer before? Maybe not. Like he was the sort of main focus of sort of physical organic stuff probably in the early 2000s, and since retired a little bit more since then. But you've probably heard things like, okay, for the relative nucleophilicity ranking of an oxygen versus a nitrogen, or a cyclic nitrogen versus something else. There's probably something you've heard where you've put some different groups in some kind of a scale, and we have some degree of certainty that changing that substrate will have some kind of an outcome in a reaction. Herbert Meyer was the one that did all of this, and the way that he did this was coming up with this idea called nucleofugacity and nucleophilicity. So the measured orders of nucleophilicity really came from his work. The big thing he came up with was taking this idea of linear free energy relationships and expanding it in sort of two directions. First, he had to come up with a way of saying, I need a very fast reaction that's going to come up with a simple way of titrating a concentration. So he came up with these stabilized carbocations, which had color, and if you add a nucleophile to those systems, you get a very rapid disappearance of the color. So it's a really quick way, very cheap, in order to use a colorimetric assay to say how fast is my red color disappearing, right? So that's step one. Step two, he wanted to say, okay, for a series of these electrophiles that have these kind of properties, I want to try and rank them where I'm changing which nucleophile. Now the problem with this kind of pairing and matching, different nucleophiles will respond and react to different electrophiles in very different ways. Remember, this is not a simple, we can't isolate just the nucleophilicity of a system. It has to involve this pairwise mechanism of an addition between two different components. So what he was trying to do is say, all right, if these are all the potential nucleophiles I'm going to use, and it ranges everywhere from anionic type systems over here, actual hard nitrogen nucleophiles, over up to species like these kind of enols, enolates, Friedel-Crafts kind of nucleophiles. So this is a huge scan of both carbon-based nucleophiles in the system. What he recognized is he needed to have a series of electrophiles that could actually span such a wide variety of different rate constants. So the problem you run into is, if you had a molecule like this with a certain nucleophile, it would actually be so slow that it's actually running on the time course of like the Big Bang, versus very, very, very pissed off electrophiles like this. Those are appropriate for measuring reactions, the fastest ones on sort of the nanosecond time scale. So what he did is come up with a whole host of these cationic species. Every one of them has this property of being a colored species to begin with as a cation, but each of them has a relative rate that allows you to have sort of different windows of time of how fast you would sort of use it. In other words, if I've got a really powerful nucleophile, I'm going to go down to something on the nanosecond end of the scale because that's sensitive enough to measure these very rapid things with very weak nucleophiles. However, if I've got a very powerful nucleophile, I'm going to go to the other end of the scale and pick an electrophile that's not as dominant because I can use that to measure relative rates of something that would normally be very, very slow. Yeah?
What is a Google hoop?
A what?
Oh, on the time scale there. Okay.
That's your homework. Go look it up. Herbert Meyer is German.
It's a kind of cake that's like donut shaped.
Yeah. See, he's a great guy. Herbert is like he embedded all these things in his papers, these little Easter eggs and stuff like this. Besides the baking question, all I wanted to lay down today was number one, you guys have seen linear free energy relationships before. Number one is these are actually quantitative. You can use them in ways to actually extract quantitative relationships. And we're going to be doing that as we jump into what Herbert did in this point and some experimental examples from our stuff. Three, too, is that, to your point, We started off by saying single parameter, electrophilicity in this case, or something like acidity. And now you can start to actually build this up into, well, what if I'm actually going to add multiple factors such as resonance, electrophilicity, nucleophilicity, all those different factors including sterics, and I'm still trying to find linear correlations. So this actually starts to fall over kind of what we did with the modeling, where you're going to have a series of individual parameters, and you're saying that this particular reaction is 90% influenced by resonance effects, but also 10% influenced by steric effects. So this is where you can start to bring together multiple of these linear free energy relationship values and actually stack them together to say, I can start to piecewise decompose a reaction and say, this is primarily controlled by sterics only, because that's the linear relationship I'm actually fitting. It gives you a huge amount of power. And where it really matters, again, just as a level set, now that we live in the area of machine learning and data science, this is where it really becomes powerful, because you have a way of teaching an algorithm numerically what an amine group is, right? You have a way of actually saying, from a representation like this requires a chemist to look at that and say, oh, well, that's fast, that's slow, that's electrophilic, but you're actually giving a systematic way to a mathematical representation to something like our molecules and actually putting them on a linear scale you can actually use for predictive science stuff. We'll kick that off with some experimental examples on Friday. So talk to you guys then.